Okay. Okay, so a black box predictive model is a formula that's either too complicated to understand or it's proprietary, which means we have no idea how complicated it actually is. Okay, so what happens when you use a black box? Well, the first thing is that you could get several years extra prison time. This is the story of Glenn Rodriguez. He was sent to prison at a young age for a crime he committed as a kid, and he was denied parole like 17 years later. And why is that? It's because somebody had incorrectly entered some information into a black box predictive model that was being used to predict whether he would commit a crime in the future. And at the parole board hearing, he was just denied, and he compared his score sheet afterward to someone else's score sheet and noticed an error in his criminal history features. And the model had up to 137 factors in it. And so it really wasn't that easy to spot an error. Now, this same situation probably happens to a lot of people with the same model. This model, the COMPAS score, is widely used across the criminal justice system. And typographical errors, they happen regularly in these score sheets because people are hand entering the information. If the model was interpretable, then it probably would have been much easier to spot the error. Okay, so what else could happen to you as a result of a black box model? Well, if you lived in California during the wildfires in 2018, you might have been using Google's daily air quality predictions to determine whether it was safe to go outside. You might have seen Google's predictions that air quality was fine on days when people were also seeing a layer of ash on their cars. Because during the wildfires, Google replaced the EPA's Trustworthy Air Quality Index with a proprietary machine learning model from the company Breezometer, which claimed to be more accurate. But clearly the proprietary model was not doing what it was supposed to do, and it put a lot of people in danger. Okay, now I've given just a few things that have gone wrong with black box models, but there's a tremendous amount more that could go wrong, and probably many things have gone wrong that were hidden, so I don't know about them. And now people are starting to use machine learning for medical decision-making, for loan decisions, self-driving cars, and all manner of other things that you really don't want to go wrong. And some people love their black boxes. They argue fiercely that they need them. Anyway, an interpretable machine learning model obeys a domain-specific set of constraints that makes its computations easier to understand. So it's a model that is constrained. And I have a more technical definition, but essentially it says the same thing, and it just gives some more examples of what kind of constraints. You could have monotonicity, causal constraints, physical constraints, like underlying differential equations, whatever it is. Now there's a spectrum between kind of loosely constrained models that are maybe monotonically increasing along one variable, for instance, to models that are very tightly constrained, like very sparse models where you understand how the variables interact with each other to form the final predictions. Now, how are interpretable models supposed to work? I want to give you an example. This is an example of seizure prediction in critically ill patients. So these patients are in the intensive care unit of a hospital. So let's say the patient comes in. They have an aneurysm that burst, okay? So in other words, this thing burst in their brain. They have a hemorrhage in their brain. And the patient goes into the hospital, gets surgery to fix that hemorrhage, and then ends up in the intensive care unit being monitored for the possibility of brain seizures. And these seizures are not like outwardly, it's not like the patient shaking, these are seizures only in the patient's brain. And these seizures actually can cause more damage than the initial hemorrhage itself, like the initial injury itself. And seizures are common. They occur in about 20% of these patients. And the only way to detect and predict seizures is with continuous EEG monitoring. However, EEG monitoring is expensive and it's limited. There's a lot of times there's not enough monitors to go around, or there's not enough people to read the monitors. And so allocation of these monitors is very important. The monitors also end up staying on people way too long. And so people who actually really need them don't actually get them. And then finally the doctors maybe put the monitors on and then they're like, oh no, this patient is at risk for seizure, or the patient had a seizure or something like that. So that's what we really want to do, is just allocate these allocate the EEG monitors correctly, be able to predict seizures in advance. Okay, so we designed a model called 2 helps 2B. It's an unusual model because it's an interpretable machine learning model. In fact, it's small enough that it can fit on a PowerPoint slide. However, it's as powerful as our best black box machine learning models for the data that we have from the EEG Monitoring Research Consortium. So I'm going to show you the 2 helps 2B score here. It's really simple. It's called 2 helps 2B because it's 2 HELPS and then 2 points for the B. Okay, so the doctors can memorize the model just by knowing its name. And then the total score goes into this risk calculator here. So if you get a score of 3, you get your risk of seizure in the next 6 hours. Now, the 2 helps 2B score was not created by doctors. This is an actual machine learning model that was created from data fed into a machine learning algorithm. It's just as accurate as any black box model you could apply to the data set, as I mentioned. It doesn't force you to trust it like a black box model does. Doctors can decide whether or not they want to trust it. Right? Interpretable machine learning models enable trust. Also, doctors can calibrate the score with information not in the database. The doctor can say, oh, I think the patient, there's one more thing about this patient. I think that's worth about a point. I'm going to add a point and then go from there. Now, we trained 2 helps 2B. I know 2 helps 2B has only a few variables in it, like 6 or 7 variables, but we trained it from the database of over 70 variables. So the sparsity came from the optimization. Now, I want to show you the algorithm that created the 2 helps 2B score. It's called RiskSlim, or Risk Calibrated Super Sparse Linear Integer Models. And RiskSlim solves the following formulation. So the first term here is the logistic loss, which keeps the model accurate. And the second term is a sparsity term that just says, can you please keep the number of terms in the model small? And then there's a set of constraints here, which says that all of the coefficients have to be integers between -10 and 10. So in other words, this problem, the feasible region is actually on the integer lattice. Now, if you're an optimization expert, you might look at this formulation and say, are you nuts? Because this is a mixed integer nonlinear program. If you tried to put this into a MinLP solver, you would not finish until maybe the end of the universe, if you're lucky, even for a relatively small data set. But the point is that this is the problem we want to solve. This is a problem of computer scientists and optimization experts. It should not be a problem of doctors who are creating these kind of scoring systems by themselves, right? So we developed some specialized techniques to solve this particular optimization problem, which is a combination of cutting planes and branch and bound techniques. And our method actually is able to solve this problem within a reasonable period of time for, data sets that are not enormous, which medical data sets are not enormous. And so that's how we created the 2 helps 2B score. So now when the patient comes in with their aneurysm and their hemorrhage and gets their surgery and they're being monitored, the doctor can look at the EEG score and say, oh, this patient has this, this, and that. Their 2 helps 2B score is 3. We're going to put them on continuous EEG for at least 72 hours and start them on preventative medication for seizures. Now, so far, the 2 helps 2B score has been validated on an independent multi-center cohort. I wasn't part of the validation study. The doctors that I work with did this on their own. They gathered data from different hospitals than the model was trained on. And they have implemented it in several different hospitals, including Wisconsin and MGH and so on. And in the first year that it was used in practice, it resulted in a substantial duration of EEG monitoring per patient, which it was really helpful for them because it allowed them to monitor a huge number more patients than they previously could. Now, there was also some cost savings, but the doctors tell us that the real savings is to be able to monitor more patients and to prevent brain damage and to prevent death. And so, in any case, that's how interpretable models are supposed to work. We're supposed to be able to take our machine learning models and put them in intensive care units, put them into these very high stakes decisions and be able to have people decide whether or not to trust them. But, don't they lose accuracy? Because since they're heavily constrained, you'd think that models, that are so sparse or so heavily constrained would lose accuracy. And it turns out that that's not actually true, right? You'd think these constraints would do damage to accuracy, but the constraints seem to work in a way that's somewhat orthogonal to accuracy. I want to go back to the COMPAS score. Now here, this is again a black box model that's used in the justice system that was constructed by a company whose job it is to construct these models from hundreds of factors of information about criminals. And you'd think that their black box would be more accurate than a very simple machine learning model trained on only a few features. But that's not actually even usually the case. That's not always the case, not even usually the case. So a few years ago, there was an article that came out by the ProPublica group, very well-known article, criticizing COMPAS for its fairness issues. And that article provided some data. They provided COMPAS scores and a few pieces of information about each person. And so we took that data and we sent it into our latest machine learning method in the lab at the time, which was called CORELS. And CORELS is a method for optimal decision trees. It tries to produce certifiably optimal one-sided decision trees that are called decision lists. Anyway, so we sent this criminal justice data into this algorithm, and it produced a model that was so tiny that it fit in the bottom of a PowerPoint slide. Now the model looks like this. It says, if you're young and you're male, predict that you'll be arrested within 2 years of your COMPAS score calculation. Else, if you're a little older and you have a couple of prior offenses, then predict arrest within 2 years again. Else, if you have more than 3 prior offenses, then predict arrest within 2 years of your COMPAS score calculation, otherwise predict no arrest. And we looked at this model and thought, there is no way that that model can be as accurate as this black box that's trained with up to 137 factors, trained by this company who had a lot more data than we did. However, we were wrong. So I'm showing you here the prediction accuracy of COMPAS and CORELS, and this is over 10 folds of the data from Florida, from Broward County, Florida, that I mentioned. And so each color is just a different fold of the data. As you can see, the methods are about equally accurate, even across folds. And what's even more interesting is that it doesn't seem to matter which machine learning method we use. They all perform the same. And some of these are really black boxes, like, COMPAS, which is proprietary, but we also have boosted decision trees, which definitely couldn't fit in a PowerPoint slide. Support vector machines with radial basis function kernels, random forests. You're not going to be putting those on a PowerPoint slide. But there's not really any way to really do better than this as far as we can tell. And so, at one extreme of these black boxes, and on the other extreme is CORELS, whose whole model is right here in the corner of the slide. And now, there was this huge debate about the algorithmic fairness of COMPAS, but the truth is that we just don't seem to need COMPAS at all. So why are we still using it? Okay, so far I just talked about interpretable machine learning and how it doesn't lose accuracy. Now, explainable machine learning is very different than interpretable machine learning. So explainable machine learning, so interpretable machine learning is about 50 years old at least, whereas explainable has only gotten popular in the last few years. And the idea with explainable is that you start with a black box and then you explain it afterward by either creating another model that approximates it, or you compute derivatives of it, or you visualize what part of the input the model is paying attention to. You essentially create an excuse for why it's okay to trust that black box, or why it's okay to use that black box, because you think you understand it because you have some kind of explanation. Now, when this field started to explode, I got a little bit concerned. And then at some point, when I realized that everybody was doing this, I got quite alarmed. And so I realized that I really needed to explain that there's quite a chasm between designing a model that is inherently interpretable versus explaining a black box. They're very, very different from each other. And here are some of the reasons that I've given people for this. The first one is that when you explain a black box, you have to rely on two models rather than one. So the black box and the explanation, and you have to troubleshoot both of them. And those models have to disagree with each other. Because if they don't, then you could simply throw out the black box and use the explanation as its own inherently interpretable model. So they have to disagree with each other. But then how often do they disagree with each other? Now, if a lot of people think that an explanation that's right 90% of the time, they think that's good. But the problem with that is that 10% of the time you can't trust the explanation, and then you can't trust the black box. So it ends up in this giant mess where you're troubleshooting two monsters instead of one interpretable model. Also, regardless of whether you're explaining black box or not, you still have this issue with typographical errors that I mentioned. So if you have a high stakes decision that relies on a survey where information is entered by hand, it's much, much more difficult to check if it's a black box, regardless of whether you have explained the black box. And then I think the most powerful argument is that if you can produce an accurate interpretable model, why should you explain a black box? So in other words, why are we using models like COMPAS when we could use something simple like CORELS? Now, I'm not saying we should use the CORELS model in practice in criminal justice, but I'm saying that there's definitely not any reason to use the COMPAS model. Okay, now another issue is terminology. So people often use the word explanation to mean approximation, but those two things are not the same. Just because you've approximated a function doesn't mean you've explained it. And the main issue with that is variable importance, right? Approximations don't get variable importance correct because of correlations between the variables, right? If you have two highly correlated variables, you can have approximation that depends on a different set of variables than the black box. So I'll give you an example here. Here's my black box, which is this curve here. And then I've approximated it with this linear model, which is supposed to be simpler, right? Now, it's definitely possible that the black box depends only on age and number of prior crimes, whereas the explanation depends on age, number of priors, and race. And then you could conclude then that the black box, you could incorrectly conclude that the black box depends on race. And you might say that that's pretty stupid. Anybody who understands the difference between correlation and causation or anything like that would actually understand that this just couldn't possibly happen in real life. But it actually could, and it actually did. And in particular, it happened with COMPAS. The ProPublica article itself that produced the data for us and led to a huge field of work in algorithmic fairness actually made this exact, did this exact thing where they approximated COMPAS approximated the black box of COMPAS with a linear model. The linear model depended on race, and then they declared that COMPAS depends on race. Okay, so here's just the title of the article. Maybe some of you have seen that, but yeah, they did exactly this thing that I was talking about, where they approximated COMPAS and claimed then that COMPAS depended on race. So let me give you a little bit more detail about what they did. The first part of their analysis showed that false positive rate and false negative rate varied by race. And they then suggested that this might not be a good comparison because the Black population in the data set was different than the white population in the data set. The Black population was younger and had more prior crimes listed. So you really needed to condition on age and number of priors because of systemic racism in society, age and number of priors are actually correlated with race. So they said, fine, we're going to condition on age and number of priors and re-examine. So what they did then was they created this linear model that depended on age and number of priors and race. Okay, so they still found a linear approximation to COMPAS with a low p-value for the race covariate. And then they concluded that COMPAS depends on race. So here's where I think they went wrong, which is that we don't think that COMPAS has a linear dependence on age and number of priors. And so their conclusion that COMPAS depends on race doesn't follow from their analysis. Okay, so I want to show you why ProPublica's analysis was particularly bad. So we took the data that they provided, like luckily ProPublica actually provided data so that we could replicate their analysis and see what happened. So they gave us data from Broward County, and I wanted to know what was inside COMPAS too, right? So I wanted to check this model out, right? If I'm going to say black boxes are not suitable for criminal justice, then I want to know what's inside the black box, Anyway, so what we did here was plotted age versus COMPAS score for each individual in the database. Now, there was a fairly sharp cutoff of COMPAS scores for each age. You can see that a 20-year-old would never get a score that was like, -4.5, like a 60-year-old might get. So I think that these values here on this curve might be the minimum COMPAS score values for each age. And there were a few outliers, perhaps due to typos in the database, but overall, this thing does not point to a linear function of age or even a linear step function of age. And in fact, the COMPAS score seems to very heavily depend on age at younger ages where you have a lot of people. So we were thinking, okay, so their analysis doesn't really follow because they made this linear approximation that doesn't really work. But we still are left with the question of whether COMPAS depends on age. So we said, okay, fine. So let's take this lower bound that we think is the COMPAS contribution to age and subtract it out and just look at the remainder and see if that depends on race. So now we've subtracted out this nonlinear dependence on age, and then the question is, does the remainder depend on race? And it doesn't seem to. In other words, we ran machine learning methods with and without race to see if these models need race to predict COMPAS well, and they perform similarly. So in other words, we found a model that doesn't use race that's as accurate as one that does use race. So not seeing ProPublica's conclusion here, but you're probably wondering, like, why, if you've seen the article, you're probably wondering what happened with these pairs of people that ProPublica was using to make the article seem so convincing, right? So they had these pairs of people all over the article where you had a Black person paired with a white person, where the Black person had a much lower criminal history than the white person, but they had a much higher COMPAS score. Now, how could that possibly arise? Well, the thing is, if you look at these two people in particular, the Black person is much younger than the white person. So if COMPAS depends heavily on age, that could explain how this happened, right? Vernon Prater is old, so he doesn't get the age points, right? And I'm not saying that I agree with COMPAS. I'm not saying it should be like this and should depend heavily on age, but if they had compared two people of the same age, it would have been much more convincing that COMPAS depends on race in addition to the strong dependence on age. Okay, so, they also missed this important problem that I mentioned earlier. What I think is really the key problem that they missed in writing their article, which is the fact that humans are not very good at inputting data reliably. So you have all these pairs, but it's possible that all of these handpicked pairs might have been due to typographical errors, right? Humans are just not very good at inputting data reliably. So if you have, say, 137 factors in the COMPAS score, they're entered by hand for each person. If you have even a 1% error rate, well, that'll lead you to at least a 75% chance of at least one typo on a survey. And this is really a serious disadvantage to complicated or proprietary models, no matter how you explain your way out of them. And in a lot of the data, we did find some weird data anomaly, just like the one that happened to Glenn Rodriguez. So we were looking at the Florida data to try to figure out how often these typos might happen. And we really found some, really just crazy inconsistencies in the data. Okay, so here is a table of individuals with the lowest possible COMPAS violence decile score. So in other words, these are the people that COMPAS thinks are the least likely to commit a violent crime. And it's sort of surprising because the number of prior arrests and prior charges these people have is pretty insane. And here are some of their selected prior charges, like aggravated battery with a deadly weapon, and restrict or obstruct officer with violence, battery and a law enforcement officer. All of these things it's kind of surprising that that they have such a low COMPAS violence score. And I'm just wondering perhaps that, how this could have possibly happened other than a data error. That's only the tip of the iceberg. There's plenty more people like that. So these are people with scores of 2 and 3, extensive criminal histories, extensive selected prior charges. I mean, typos are just much easier to spot if the model isn't complicated. And we even think we found typographical errors in the COMPAS documentation from Northpointe, which is the company who makes it. This is their documentation, which indicates a linear function of age in criminal history. We don't think it's linear. We think that maybe there's some nonlinear transformation. And actually, the COMPAS people responded to our article on this. They actually wrote a formal response that's published in the Harvard Data Science Review. And they sort of confirmed the fact that there was some nonlinear transformations that weren't in the manual. Anyway, so getting back to interpretable versus explainable machine learning, I'm putting up here a slide from the DARPA Explainable AI BAA. And when I saw this figure, I found it very dismaying. There were some issues with it. And the first one is that the axes, so what it's supposed to indicate is that your learning performance has to go down as your ability to explain what's going on improves, okay? So, there's this inverse relationship with your performance and your ability to explain yourself. And the first thing I noticed about this figure was that it's not from any real problem. Like, these axes are not quantified. There's no actual data set that goes with this figure. It looks like somebody sort of, drew it. It looks like Trump drew it with a Sharpie. It's just not real. It's just matheism. So I said, okay, well, let's just go with it for now. Well, what it seems to indicate is that somebody's using a number of different machine learning algorithms on a static data set with a fixed evaluation metric. But that's not actually the way we do data science. The way we do data science is to actually interpret the results after the machine learning algorithms run to see if they make sense, and then go back and change our data and perhaps update our evaluation metric. So this whole experiment is on a premise that doesn't really make sense in terms of the way people actually do science. And then even if you did even if you did limit yourself to a fixed data set and a fixed evaluation metric, the trade-off doesn't actually happen like this. It's actually relatively flat. And I showed you some examples with COMPAS where I tried many, many different machine learning algorithms with different explanation effectivenesses, and it was completely flat. And I'll show you some examples, even with deep learning in computer vision, where we can find interpretable models of the same level of accuracy as black box. And it's even flat for deep learning and computer vision. So it just depends on how you define the interpretability metric. So anyway, that's another reason why that they wouldn't have been able to find such a picture in the wild. And then the other issue I had with this image is that it wasn't clear whether they were talking about explaining black boxes or producing inherently interpretable models. Because if you were approximating a black box, you might suffer some approximation error and you might see a kind of trade-off like this. But if you're using inherently interpretable models, there's enough freedom in the data that you wouldn't see this. And so as it turned out, they were talking about explaining black boxes. So after a couple of years of this nonsense kind of continuing, I finally just got myself together and I wrote a paper for a workshop called Please Stop Explaining Black Box Models for High Stakes Decisions. And then when I went to go turn it into an article for a journal, they made me take out the word please. So they made it kind of sound more commanding, like stop doing this. And in any case, in this article, I gave a lot of reasons why you should stop doing this. And I just want to tell you some of them, which are the ones I've already kind of explained through, namely typos. There's no way around the, you can explain the black box all you like, but you're still going to have typos if it's too complicated. And then black box models still force you to trust the data set. I've never met a large data set that didn't have a serious problem with it of some kind or another, some serious bias or some weird notation and there's some confounding, something like that. There's this issue of double trouble that I mentioned where you now have to rely on 2 models instead of 1 when you explain a black box. Those models have to disagree with each other. And then this issue of terminology, that explanations are just approximations and they don't even need to use the same variables. So you might mislead yourself into thinking that the black box depends on something when it doesn't. And I give you the example of ProPublica to kind of demonstrate that. And then, of course, the most powerful argument, as I mentioned, is that if you can produce an interpretable model, why should you be explaining black boxes? Do you really want to extend the authority of the black box? Now, I want to get into a little bit of nuance on this idea of not losing accuracy for gaining interpretability. And there's really 2 types of problems in machine learning. There's tabular data problems and raw data problems. So tabular data is where the features are interpretable, inherently interpretable, and each feature is like a decent predictor. And somehow most of the data sets in my career that I've encountered happen to be tabular data. But I have made an effort to kind of work on raw data problems as well. So raw data problems are things like computer vision, where you have like each pixel is a dimension. So each pixel itself is not really a meaningful predictor of any kind of, what is in the image. Or maybe bits of a sound wave or words in a very large document. Now, for raw data, neural networks are really the only technique that's working right now. That doesn't mean that they can't be interpretable. I'll talk to you a little bit more about that. Whereas for tabular data, all the methods tend to perform very, very similarly with enough preprocessing. And I showed you an example of that with COMPAS and CORELS. That's pretty much what happens with tabular data, is that they all kind of perform the same. So I want to get into this a little bit further. And as I said, it seems to be not true that when you add these extra constraints that we're losing accuracy, but it really depends on your ability to choose a good definition of interpretability. And in most cases, when you do that, you actually can understand what's going on. And that level of understanding actually helps accuracy and not hurts accuracy. So the trade-off is actually going in the opposite direction, where you're actually gaining some benefit in accuracy by understanding what you're doing. So I want to just kind of finish up by talking about the possibility of an interpretable deep neural network. I actually have a couple of papers on interpretable deep neural networks. I'm going to talk about one of them today, which basically tries to do essentially PCA for neural networks. It's a way of disentangling the information that flows through a neural network. And this paper is called Concept Whitening. So this is Zhe and Webster who worked on this paper. And I want to show you what concept whitening is designed to do. All right, now convolutional neural networks for computer vision are not naturally disentangled. So you wouldn't really see that one node would like you'd love it if all the information about airplanes flowed through one node and that all the information about cars flowed through another node so that the information was disentangled on the different concepts. But CNNs don't do that. They actually, the information about concepts flows kind of all the way through the network. So the information about airplane might go through all of these different nodes in the network. Okay, so what people have decided to do is they've decided to try to explain the neural networks by creating what are called concept vectors. So a concept vector points in the direction of the neural activations toward a concept. So for instance, let's say that we're talking about airplanes here. So as it turns out, whenever airplanes happen to show up, neuron 1 and neuron 2 are both highly activated. So in that case, we would put a dot right there for that image of whatever it is. So this image of airplane that has an airplane in it, it highly activates on neuron 1 and neuron 2. And then these images that have car in them, they activate also on neuron 1 and neuron 2, but less so on neuron 2 than on neuron 1 or something like that. So anyway, people have been trying to create these vectors that point toward the different concepts to try to explain what the neural network is doing, what part of the latent space is handling which concept. But the problem is that it doesn't really work. And the reason is because the concepts are not disentangled. So the vectors are not orthogonal, or they're not orthonormal. So you might have the case where the airplane vector and the car vector are pointing in the same direction, which is not what you want. Right? What you'd really like is for the airplane, all the information about airplanes to kind of go along this axis, and all the information about cars to go along this axis, so that when you're wandering around in the latent space, you know exactly how much airplane and how much car is being considered for a particular image. Okay, so we designed this substitute for a BatchNorm layer, BatchNorm step. It's called a concept whitening module. So you take it to BatchNorm and you put CW in, and CW does what the BatchNorm operation did, but more. Okay, so again, it's doing something like PCA, but more sophisticated. It's actually disentangling this latent space. Okay, so when the CW module is added to a convolutional neural network, the latent space is whitened, so it's decorrelated and normalized, and the axes of the latent space are aligned with the concepts of interest. So it would decorrelate the space and normalize everything, and then it would rotates space so that the concepts lie along the axes. Now, CW, I want to show you a little bit about what it does after you run this thing. Okay, so remember, CW forces all the information the network uses about airplane at that point in the network to go through only one node. So what information could the network possibly be using when you're only like 2 layers in? Okay, so let's just talk about the beginning of the network. Now, the network can't possibly represent an actual airplane in 2 layers. So what it does is it forces all the information the network needs to detect, say, airfield. Using airplane, it focuses that to go through only one node. It's like trying to construct a primitive version of the airplane that it can use to detect airfield. And let's look at what it thinks is the most extreme version of airplane. And as you can see, none of these are airplanes, which is what's so interesting about it. It's like a primitive airplane happens to be a gray object or a white object on a blue background. And that's 2 layers in. That's all the network. That's all the information the network is using about airplanes 2 layers in. And it's all feeding through this one node. And it does the same thing for other concepts too. Like for bed, it seems to really like warm colors and busy textures. To detect person, it likes kind of linear textures, I think. It's really interesting, like these primitive notions of these concepts that the network is using to detect its final end goal. Here, the end goal is scene detection. So it's detecting things like airfield and bedroom and so on and so forth. Okay, yeah, so in early layers, color and texture information related to the concepts are represented along the axes. Okay, so if we move the CW module all the way to the 16th layer, then you can see that it's actually showing that it's able to represent an airplane because it's gone through 16 layers. And so at this point, what's going through that airplane node is actually representing airplanes. The most highly activated images along the airplane axis are actually airplanes, and beds for the bed node and people for the person node. Okay, now I want to show you how an image moves through the layers, how it travels through the layers. So let's take this image over here, which I think is really interesting. This is a picture of a sunset. So it's not an airfield and it's not a bedroom, and it has neither a bed nor an airplane in it. But it does have a sky, and it has the bright orangey colors that the network is using to detect bed. So in very early layers of the network, it thinks this image is a bed and not so much an airplane, because remember, in early layers, an airplane is blue background with a gray object in the middle. So the network starts out in early layers, and all the information that's going through this, there's the bed node and the airplane node, and the bed node is like, wow, lots going on, and the airplane node's like, nope, nothing here. And then, as the layers continue, things change. The network is able to create more sophisticated representations of these concepts, and then it's realizing that maybe there's not really a bed here. And then it's thinking, hold on, I see a sky. Maybe it's an airplane. And so it's kind of wondering, okay, what's it gonna do now? And so then it's thinking, well, it's meandering around a little bit and saying, yeah, there's definitely an airplane here now. I'm seeing clouds and stuff like that. And then eventually it decides that it's not sure whether it's an airplane, but it's definitely not a bed. Anyway, so some advantages of CW over BatchNorm are that it doesn't seem to have any sacrifice in accuracy over BatchNorm. Doing this replacement with the CW layer doesn't really affect accuracy. The accuracy is on par with the standard CNN baseline that we started with before we replaced the BatchNorm with CW. And it's really easy to use. You just take your pre-trained black box, and then you do one additional epoch, meaning you run through each of your training examples once to update the network, and that's it. I will say there is somewhat of a bit of extra work, because you actually have to define the concepts. You need to have data that allow you to define the concepts. So you need to have a bunch of pictures of airplanes and a bunch of pictures of beds and so on and so forth. So you do need those extra kind of data sets. And then, but you get it for free. It actually disentangles the latent space for you. Okay, so just to summarize, predictive models are everywhere. They are in lots of high stakes decisions, including criminal justice, air pollution, allocation of health services, health treatment, recommender systems. They're going to be in self-driving cars. Don't we want to be able to troubleshoot them? Don't we want to detect if they're biased in a harmful way? Don't we want to be able to ensure that a typo didn't make a decision for us instead of a judge? Don't we want to be able to use these models in high stakes decisions like the 2 helps 2B score? Or do we just want these models to kind of languish on the shelf? Don't we want to be able to understand these models? Anyway, that's it. That's all I've got. Thank you.